guess this is like the Thanksgiving lecture, right? So everybody's gone. What's that? This is like the Thanksgiving week, so that's probably why no one's around. The project's going good? Yeah? Any questions? Yeah?
The numbers on the assignment, they say like we got this amount. Is that just sort of ballpark where we should be, or is that like if we've done it correctly, those are the numbers we would get?
You should, yeah.
Those are lower bound, so we should be doing better. Okay. We took what we were getting and we actually gave you a few. The path lengths are correct, however. Path lengths are correct.
So we rounded down.
With the average reward, it's a little lower than what we should be getting.
That's kind of the funny thing about these algorithms. Like if you do something almost right, like it learns, so it kind of corrects. Like it'll still do something often, even if it's not doing the optimal thing. And like, it's funny, like when we're recording them up or something, it'll get to a point where it's doing better. Like it's learning something, but it's maybe not learning as fast or not converging to the optimal policy. And so, thinking through that can be fun because it's doing something good, right? But it's still not like doing something optimal. That's where the theoretical analyses become important, because then you can say, well, I'm not done debugging this code because the math that I did said that it should be working better than it actually is working. Any other questions before we get started? Cool. So this is we're kind of this is like a little mini unit at the end of RL about robotics. So what I thought would be kind of fun is to kind of talk about some of the work that I've done in this area that kind of puts the pieces together of what we've covered in different parts of the course in different ways. You can kind of see how the different ideas that we've discussed can get implemented and used to do real things on one application, which is robots. The next class is going to be, so Thanksgiving is Thursday, so no class on Thursday. Tuesday is going to be the final review, and then the following Thursday and Tuesday are the final exam. What's funny, is it? Too fast. You want more AI? So actually, if you do want more AI, there's a lot of, we can, maybe I'll talk about this more at the final review, but there's good follow-on classes. So Eugene Charniak is teaching his computational linguistics course. In the spring, we have a number of really strong computer vision researchers in CS and also engineering and CLPS that I'll teach classes. I don't have them all in my head like when they're offered, but like you can take computer vision, you can take machine learning. And then I also encourage you to check out people's graduate seminars. So I'm teaching a graduate seminar in the spring semester about interactive communication between humans and robots. And those can be, if you're interested in research, those can be a really good opportunity to become familiar with a particular research area. They can be hard to find because a lot of the specific topics are really cool but not well advertised to the student body. So those are really good classes to shop if you're interested in going farther. Another thing we're going to do is we've been using this AI lunch thing. I've told you about it a few times during the semester. In the spring semester, we're going to use the AI lunch for a kind of research speed dating service. So like we're going to have a bunch of people in CS who have research projects where they're looking for undergraduate help or collaborators. They're going to give a pitch of their project, and we're going to invite you guys and also other undergrads, like every undergrad in the department to come. And if you're interested in joining a research project, in AI, that's a really good way to find out more about what's going on. Any other questions before we get started? Okay, so robots. So this is kind of like I kind of think it's like the ultimate version of like our general algorithm for AI, right? We want something that can act rationally. And if you're a robot, you're a physical creation that's operating in the physical world. You're looking at noisy sensor information, and you guys did the SLAM project, so you kind of know what that's like, to try to figure out what's going on out there in the world. And you might have a noisy estimate or idea of what you're supposed to do. So like this idea of scoring, well, maybe the reward function, but you might even know what the reward function is, right? Like if your job is to make the person happy and you don't really know what the person wants, it's a challenging problem to figure out what the person wants. And then, even if you did know what the person wanted, it's a challenging problem to figure out where you are in the environment and what actions you should take in order to meet the person's needs. The reason I like robotics is because everything has to work in order for the robot to do everything, like all the way down to like the network, and your hard drive can't crash, to having a good algorithm and having good training data, to the high level of like having a planner that's doing the right thing and figuring out what's supposed to happen. It's also the reason I hate robotics, because everything has to work, or else your robot doesn't work. And if you've ever seen, like, there's a kind of, it has a reputation for like, lots of times robots are broken, and that's why, because it's so hard to get everything to work at the same time. So this is an example of a robot. I think I've shown this to you before. It's the forklift. It's got sensors, it's got actuators, it's doing drive-by-wire. This was created by a team at MIT, led by MIT, but a lot of other places collaborated to make this platform, this robot. And it can do stuff for people. So it's designed to operate in Army warehouses. They're called Army SSAs, which stands for Supply Support Activity. And it's basically a warehouse. And they can autonomously do things like unload trucks and move things around into different storage areas. And this is important because when we have like forward operating bases in dangerous places, we don't want to put people there. So if you have more autonomy, then it's, if bad things happen to that forward operating base, people's lives aren't at risk, just the robot, which may be expensive, but it's not the same as somebody's life. So as we have these systems that become autonomous and powerful and capable of doing useful behaviors, there's a real question, which is, how are we going to tell them what we want them to do, right? So like, how are they going to figure out what the reward function is that they're optimizing in the first place? So these are some examples of robots, the forklift there. I think I showed the slide at the beginning, but I think it's still cool to see robots, right? This is a robot made by undergraduates at Olin College that can drive around autonomously outdoors in GPS-denied environments. A lot of ground robots use GPS to figure out where they are. This robot doesn't need GPS. This is a helicopter robot, can fly around in indoor environments, so no GPS there either. And it uses SLAM, the same localization and SLAM kind of ideas that you guys coded up for your project, this robot uses to localize itself as it's flying in the environment. So that's good when it's flying slowly and straight. What do you think happens when it's like flying fast? When it flies fast, it's got to like basically tilt to make its rotors go. So what do you think happens? The LiDAR is like this, so it tilts. Here, I'll turn my laser pointer on. Yeah, right. So if I'm doing SLAM on a ground robot, you can see my laser pointer on the wall. I'm at a fixed level, and I'm good. If I tilt to go fast, my LiDAR doesn't work. And the same group actually did some work with a plane, which is the same thing, only you can't really fly slow with an airplane. You fall down. A helicopter can stop and hover and think. An airplane, if they stop and hover, it's going to land. And the whole way that it turns in an airplane is like by banking. And so the LiDAR doesn't work. If you have a 2D map of the environment, you don't know where you are when you're turning. So they had to make new SLAM algorithms, localization algorithms, that figured out, when I turn, I'm not going to know where I am, so I better make sure I go straight for a while after that to get a good localization, and then I'll turn again. But if that better be okay. There better not be a wall or something while I'm going straight, because then I'll hit the wall. Yeah.
Does it rotate their sensor when they
Yeah, so that's a good idea. Yeah, another solution would be to have a 3D map, right? So the map you guys were using was like a 2D map, right? So there was just occupied and unoccupied. And that is the sort of canonical representation of a map for a ground robot. And there's another active area of research in SLAM right now is like this idea of 3D maps, right? So if I have a connector, have we talked about what's it called? The Velodyne. No? Okay, so if you've ever seen a Google car, it's got, I think there's a picture of a LiDAR. Actually, it's right here on this forklift. This is a LiDAR, the laser rangefinder for the forklift that works in outdoor environments. The Velodyne is this LiDAR that basically, it's mounted vertically, and it spins around in circles, okay? And if you actually see a Google car driving around, you'll see on its roof is a Velodyne, and it's actually spinning in order to aim the laser in different directions. So you get 3D point cloud with very high accuracy from the laser rangefinder. And that's what the Google car uses to not hit stuff in the environment. Anybody want to guess why that might not be the best idea for the helicopter? Yeah. Yeah, right. So that might like make the control a little harder. And there's one more reason, which I didn't even realize until I started hanging out in the lab that was doing this. So this thing can fly for like 15 minutes. And one of the main limitations, so what do you think, what does that make you think of things when we talk about putting more stuff on it? What's that? It's more heavy, yeah. So you're in this like battery world. Like I have more batteries, but batteries have weight, so I can't fly as long. Right. So people worry a lot about they call it payload, right? Like you want your sensors and actuators to be as light as possible, so that you can fly for as long as possible. And I was just at a meeting where they were showing, it was a company, and they were making quadrotors to fly around outside. And what they had was like a base station where the quadrotor would land, and it would automatically swap out the battery, and then it would take off and fly again. So that 15-minute flight time wasn't like a killer. Like you landed, and then this machine would come in and like swap the battery, and then it would take off and fly off again. So these heavier sensors, like the motors that you need to spin around in circles, people are less happy about them because of that. So people are also investigating monocular cameras on these types of vehicles. Again, like the sensor isn't as good. Like the LiDAR gives you very high accuracy data about how far away you are. So it's harder to use the vision data, but the sensor is really light. So if we can figure out the algorithms to let it do localization and mapping with a monocular camera, like on your cell phone, for example, then we get a boost for how long these things could fly. Cool. All right, so there's a lot of work on like interfaces for how you tell robots what to do. There's a lot of work on all areas of robotics. Like a big area is like just making them do useful things. But to narrow it a little bit, we can think about like existing approaches for telling robots what to do. So one of the most common interfaces is something like this, where you've got a little controller. Or PR2 at Brown has a PlayStation controller, and you can drive the robot around with that. You can see the guy here is using something kind of like that, a joystick-based interface. What do you think is good about that kind of interface? What are some good things about it? Yeah, you have pretty fine-grained accuracy. It's going to do exactly what you tell it to. What else? What else is good? Yeah. What's that? Yeah. So people say like if you pick up that PlayStation controller, you can just immediately start to drive it. If any of you came to NERC, they had a joystick interface for the arm. If you remember it, I don't know if some of you saw it. There was this robotic arm, and you could control the position of the arm in 3D space. You can move it up, down, left, right, and control the pose. And little kids were coming and playing with it, and they were able to move the arm around. It's pretty intuitive. So these are nice for that reason, and almost all robots come with them. This PackBot interface is used. Anybody know what this interface in the back there is? This robot is a PackBot. It usually comes with an arm. And anybody know what it's used for? Ever heard of PackBots? Yeah. What's that? Yeah. So the PackBot is a robot made by iRobot. They make, what else do they make? What? Roombas, yeah, the Roombas. There's like more Roombas, the most common robot in people's lives is the Roomba. And iRobot makes it. But they don't make much money off of the Roomba. Their margins aren't very large. They get much larger margins for their military contract. So the PackBot is a robot that's used for disarming IEDs, improvised explosive devices. And if you actually go visit their office, they have a sort of half-destroyed PackBot that was blown up in, I think it's Iraq, one of those places, by an IED that it was disarming. So a soldier will drive the robot in, and they'll stay far away, and they'll very carefully kind of poke at a pile of debris and try to see if it's something dangerous or something not dangerous in order to disarm these devices. And they're using an interface like this. This is actually an older version. I think they actually use PlayStation controllers now to control the robot and do stuff. Okay, so then in the middle, there's this picture of like a touchscreen interface. And this is what they created to control the forklift. And they use something like this also in the Google car, where there's like a tablet and you can like select where you want to go. And so with this kind of interface, it's not like a PlayStation controller where you're like actually moving. You might be actually moving joint angles on an arm. Or like one level up from joint angles is like moving the position of the arm in 3D space. Right? So you have to do some math to do that. Like if you want the end effector to be here, there's some set of joint angles at my elbow and at my shoulder that I have to find to move my end effector here. That's called inverse kinematics. And they might not be unique, right? Like if if I keep my end effector in the same place, I can move my elbow up and down. And so these are all different joint angles, but my end effector is in the same location. So you have to do some math to figure out like what joint angles you should use and stuff. That's called motion planning. The RT assignment that we made optional is about a way to do that, to find a plan for your joint angles to get your end effector to different places. So here, this robot has more autonomy. So when you use this touchscreen interface that they created, you can tell it at a higher level, like, well, I want you to pick up this pallet. You might circle the pallet in the picture on the pad. And then the robot will autonomously figure out like what lower level actions it should take to like drive up to the pallet, pick it up. Then you might circle a place in the environment where you want the pallet to go. Like you might pick it out on a map or something like that. And then it'll autonomously drive through the environment and avoid obstacles and localize and do all that stuff in order to make the pallet be where you want it to be. So what's good about this? What are some good things about it?
The robot is really smart. There's less linearity.
Yeah. Yeah, so like if you're trying to drive this forklift remotely and you screw up, like you might hit something, or you might get into an accident. So it's probably safer. Like you're hoping that your algorithms are safer than the human driver is going to be. And that's actually, if you've seen that's one of the main arguments people are making in favor of the Google car. It literally has eyes at the back of its head. We have to get the algorithms right, and there's a lot of effort being spent right now making those algorithms robust. But if we get to that point, it's not going to fall asleep at the wheel. It's not going to, it doesn't have a blind spot. There is no blind spot because you can literally surround the entire vehicle with sensors and see everything that's going on. Now, compared to a person, you have to actually use that input, right? You have to process it quickly. You have to process it accurately. You have to make good decisions based on that input. But at least the potential is there. The information is coming in about what's going on all around you. And I think that in our lifetimes, I think we'll see that translating into robot drivers that have a lower accident rate than human drivers. We'll see, but I think that's likely to be true. What else is good about this kind of interface? Yeah, you just got a little cell phone in your pocket. You pull it out. You start tasking your robot. Yeah, easy, good. It's light. It's something that's just with you. What else? Yeah. 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 So you don't have to supervise the robot. You can tell it to do something, and then you can go off and do something else while the robot's doing its thing. And that's kind of getting at this goal of like autonomy, right? Like the robot is supposed to be less effort, like having the robot do it should be less effort than having you get in the forklift and drive it around and do something. Otherwise, you haven't really removed a person from this whole environment and achieve the promise of robots. So right now, like with this kind of interface, when they send a PackBot in, there might be 5 or 10 people that are supporting that robot. One robot, 5 or 10 people in the field that are like, bringing it there and controlling it, watching the different outputs that's happening. So where they want to move to, there's like this roadmap that was created, I think by the DoD or Congress, some government, some part of our government, that says they want to move to a world where the ratio is reversed. There's one person and they're controlling multiple, or they're somehow using or benefiting from multiple unmanned systems. that are operating with higher levels. In order to make this happen, they have to operate with higher levels of autonomy, because you might be able to joystick one robot around, but you can't joystick 10. It's too much effort for the person. So people are starting to think about, like, how can we make that happen? How can we task them with high levels of autonomy and come ask the person what's going on when they get stuck or something like that, but not have to give them these low-level commands. All right, what's bad about this kind of interface? What are some things that aren't so good about it? Mm-hmm. Yeah. Yeah, so that small thing, it's convenient, it's easy to carry with you, but you might not be able to see everything out there in the environment on that little tiny screen. If you have a bigger screen, then you're in this sort of trade-off about what to do. Good. What else? Mm-hmm. Yeah, so you got to carry like your battery around with you, and if you're out in the field. So this is another picture of like a field device. He's carrying this backpack to fly a robot airplane that's going to do surveillance, and he's got to carry a big backpack with the computers and the batteries and the other things that he needs in order to operate that robot. And if the battery dies, then you lose the robot. I mean, you might not lose, it depends where the robot is, but like you don't get to use the robot once the battery is dead. What else? That's bad. Mm-hmm. Yeah, that's right. So like if your robot is stuck somewhere and you've just got this high level control, you can't jump back down to the low level control, then you're stuck. You can't really use, like maybe they thought of it, or maybe not. Maybe they thought of it, maybe it's hard to drive, or a forklift. It probably is hard to drive a forklift with a phone. In the case of this forklift, they had a solution to that, which was, don't use the phone. Like what can happen is anybody can get into the forklift, into the driver's seat, and start driving it around as if it was a regular forklift, and get it out of trouble. So they didn't try to do that through the phone at all because they thought that it was too hard. But that might not be possible or feasible, especially if there's a lot more distance between you and the robot. If the robot's out somewhere far away from you and you're operating it, you might not be able to step in like that. So something people are thinking about a lot in this context is like teleoperation interfaces. So Chad Jenkins here at Brown does a lot of research in like remote control of robots where you're far away from the robot. So how can you give the person enough information to make good decisions about what the robot should do? And how can you be robust when things fail? So like what happens when your network dies and starts getting really laggy? Does the robot just freeze? Like what if it's on the highway, or something like that? You kind of have to think about how it's going to respond to when that happens. Our Predator drones are robots. They're autonomous, unmanned. They're not autonomous. Autonomous is one of those funny words. They're unmanned aerial vehicles, and they fly over places, and we use them a lot for airstrikes. And they're operated remotely by people in the United States, sitting in like basically a data center, connected over a high bandwidth link to these airplanes, and they're flying the airplanes that might be in Afghanistan or in Iraq. So they work with these kind of teleoperated interfaces. Cool. So something I usually say when I look at this slide is, what's bad about it is the person has to look down at this interface when they're using it. They're not looking out at the world, which is what presumably they care about. Like they're in the world with the robot, and they might want to look at the world and point to things in the world with the robot. And instead, they have to look down with this little tiny pen and point at things and circle things. So one of the problems I got, and this is I have this one up here because it's kind of an extreme example, because he's outside in the sunlight, and he's got to put this hood on in order to see the screen and use the interface to control the robot. So something that I've been thinking a lot about is natural language interfaces to robots, where you're in the environment with the robot. Maybe you've got a mic so you can talk to it. And it's got cameras maybe, or LiDAR, or Velodyne, so we can see what gestures you're making to the robot. And then you're saying things like, return to Camp Charlie, and then take the eastern path to the landing zone, just as if you're talking to another person. And then that's telling the robot what it should do. So this is kind of one level up on that autonomy scale, right? So like, it's not joint angles. It's not even like, selecting high-level actions. You're just going to talk to it, and somehow it's going to figure out from your conversation what you want it to do, and then hopefully it's going to do the right thing. So this is like an example on the helicopter. He's going to say, fly past room 124, then face the windows and go up. Sorry, the sound's turned off. So we speech recognize that, and then we send it to our inference engine, and it's using the LiDAR to do localization, making a plan of which trajectory it should take through the environment based on what it knows about what words mean. And then it goes off and flies on the mission. So you can kind of see down here, this is its visualization of where it is. And like the scans, the laser scans of the screen, you can see as it's tilting, like the scans kind of go up and down. But it goes slowly enough that it can stay mostly level, so regular scan matching localization can work. And then flies through the environment, turns so that its camera is facing the windows. You can see the view from its camera, and then flies up to inspect them. So you don't have to have a human pilot to tell it what to do. I'm just doing this. So that's an example of like a helicopter. For the forklift, you might imagine things like put the pallet on the truck. And then instead of poking at something, you have to figure out like, well, what pallet you're supposed to pick up. So it kind of looks like a little bit like the machine learning that we were talking about for spam versus not spam. Like there's a bunch of different objects that I might know about, and one of them is the pallet that the person is talking about. And I have to figure that out. And then like, well, which truck? Where in the environment should I take the pallet, and how do I know when I'm done? This is all coming from language. So what are some advantages and disadvantages of this type of interface? Yeah. Yeah. Yeah, so if you're operating in a multilingual environment and your thing knows English and it's talking to people, a big concern is people who speak Arabic, at least of the funders who fund this type of research, right? Like, or some other language that is not known to the robot, then those people are excluded from the system. They can't use it. Yeah. Yeah, so if something goes wrong, and a lot can go, as I said, a lot can go wrong. If something goes wrong, it might end up doing totally the wrong thing, and that might be a big deal. Like if it's a forklift, like that's a big, heavy piece of equipment, and it's moving big, heavy, expensive, sometimes dangerous things around in the warehouse. So if it does the wrong thing, that's not so good. And if there's no screen or something, you really can't tell what it's going to do until it actually goes off and does it. So it can be dangerous. Yeah. So right. So like maybe you can imagine some kind of like feedback mechanism. That's actually something I'm thinking a lot about right now in my lab. Like because of exactly that problem. Like we made the system that would follow commands, and it would basically think for 5 minutes and come up with like this thing that it could do, and it'll be right 60% of the time, which means it's wrong 40% of the time, doing the wrong thing, and you have no way of knowing. So a lot of what I'll talk about, assuming we have time, we'll make time. What I'll talk about later today is some of the mechanisms that we're putting in place to try to address that, create these kinds of feedback loops. So those are some disadvantages. Any more disadvantages? It's not like there's a finite list. Slower, yeah. It depends on the task, I think. Yeah. What's that? Yeah, right. So this system like even this helicopter system, like it takes a while for this it takes time for the speech recognition to run. It takes time to run its inference, and then it takes time to actually go off and execute it. And all of that is time that the robot is not doing what you want it to be doing. It's just thinking rationally maybe, but it's not acting in a way that you want. Yeah. Yeah, so you might, again, like these errors come because, what if there's 2 pallets or 3 trucks? How does the robot decide?
Well, sometimes the commander does not, I mean, the thing the commander says is not
Yeah.
what you want to do.
Yeah, they might just tell you something that doesn't make sense. We actually saw this in our I think the next slide is data. No. I have a data slide of like things that people said. And they're all commanding the robot to do the action you see in that video up there in the upper right. And we collected this data by showing people that video. And we said, pretend that you're talking to a person who's driving the forklift. And you want to command them to carry out that action. So it's going to restart in a second. So like right now, it's got a pallet. It's going to drive forward a little bit, raise it up, put it on the truck, and then back up and put it down. So like this simple, short, seemingly well-defined little action. And you can see all the different ways that people on AMT, on Amazon Mechanical Turk, commanded the robot to do that action. So some of them said things like, sort of short things like lift the tire pallet to the truck, but there's grammatical errors in there, right? They do things like leave out determiners. So here so this person said, lift tire pallet, there's no the, which is going to throw your algorithm for a loop. Like if you're trying to parse according to a grammar of English and you don't have a determiner, which people say, right? Like this is what people do. This is what people are going to tell to your robot. Things are going to go wrong. They break it down in really different ways. So some person said, you put the tire pallet on the trailer. That's like one sentence, two clauses, straightforward. Whereas the next person said, lift the tire pallet in the air, then proceed to deposit it to the right of the tire pallet already on the table right in front of you. They give you these much more detailed instructions, which maybe is good because this one is sort of vague, but maybe it's bad because that's extra stuff you've got to understand and extra stuff you've got to think about. Yeah. What's that? Uh-huh. Right, so people are going to use language in different ways. And the way that one person uses language is not going to be the way that another person uses language. Even if they all speak English, people have different accents. People speak in different ways. It turns out that in speech recognition, the accuracy rate for men turns out to be higher than the accuracy rate for women. And we don't really know why. It's something to do with the training data, or we don't know why, but it's true. It's true that, and it's also maybe less surprising, people with a strong accent, for whatever reason, probably because of the training data mismatch, it doesn't work as well. The accuracy is lower. They'll see more errors talking to the robot than people with the sort of not a strong accent. Yeah?
Can you remove some of these obstacles you mentioned by safely assuming that the instructors of the system are basically set up particular people, so you can come up with a shared vocabulary between
Yeah,
people
yeah,
instead of coming
yeah.
up with.
Yeah, that's a really good idea. So the one grant that I'm on, there's a team in Florida that's doing that. Like their job is to identify the shared vocabulary that people, it's an Army grant, so it's people in the Army that are going to talk to a robot that's doing surveillance and figure out what words they want to use and figure out what they want those words to mean. And then train the users to not do this, but to use words in that vocabulary and in that grammar. There's a researcher at UW, her name is Maya Takmak, and she thinks about, she calls it robot ease, right? Like what types of programming languages, almost, can we create to enable people to program robots to do complex tasks where it's not English, it's like, here's something like JavaScript for robots or something like that. There's a huge design space there, right? So that you can tell robots what to do precisely, but also at a high enough level of abstraction so you can do it quickly and easily. So yeah, good. Okay, so one big problem with language is well, how do we handle all of this, complexity in the things we're going to say? And there's obviously lots of other problems. What are some good things? Why might we want to do this anyway? Should we just say language isn't a good idea and we're just going to work on robot ease and not try to understand these types of commands?
It's a hard cut from the
What's that?
Removing the hard part from the robot, from the people to the robot. So now the robot is responsible for actually doing the thing.
Yeah. Yeah, so if we could actually get this to work, it might be pretty nice because you don't really have to learn to use an interface. You don't have to carry around something in your pocket that might have bugs. If it really works, which is a big if, but if you can really get it to work, it really opens up the robot to a much broader audience. Of course, there's these issues of language and grammar and speech recognition and stuff, but the vision, like if we can somehow solve those types of problems, it's an interface that you can imagine your grandma, your mom, or your dad, somebody who's not trained with robots, using without too much trouble. And that's why people got so excited about Siri, the iPhone interface, because you can just talk to it, and it kind of works. It's not perfect, but it kind of works. What? Chat with the robot, yeah. So that's why I got interested in language, because I felt like it was this interface, like if we could actually solve it, if we could actually get something that worked, it really broadened access to this technology. And I think that it's not like there's a silver bullet. Like I think there's situations where language makes a lot of sense, and there's situations where the PlayStation controller is absolutely the right thing. I don't want somebody controlling the Predator drones with language. We can just skip that. Like I really want somebody to be driving that and checking that every single thing that that thing does is the right thing. On the other hand, like if you think about robots in the home, robots operating in our everyday lives, that are used by a very broad spectrum of people, and you want them to be inferring helpful actions. I don't think my mom is going to have, like, I don't know, all of our moms are different, but like my mom, does not have a technical background, and I don't think she's going to have too much fun learning robot ease. She's going to call me up and make me do robot ease. But I could imagine her talking to the robot. I could imagine her saying what she wanted to do, and then if we can figure out what to do, we can get somewhere. That's kind of what motivated me to think about this language stuff. So I usually talk about one reason why it's hard is like all of the ambiguity. Like language is very diverse, and there's this mismatch between what they say and what the robot wants to do. There's another big thing I kind of skipped over about why it's hard. Which touches really a lot on AI, which people have called the symbol get running problem. And this is the problem of this mapping between words, so like these are some words, the palette of boxes on the left, and stuff out there in the world. Right? So this is a picture from a real army warehouse. This is some boxes and some pallets. They're sort of in storage. And what you have to do is somehow figure out if they're saying the palette of boxes on the left, they maybe mean that one over there in my picture, right? Like I'm going to run my door detector. I'm going to run my palette detector. You guys made a door detector for one of the projects. And I'm going to run some kind of slam that's going to do objects too, right? Like it's not just going to tell me occupancy or not. It's going to tell me where it thinks all the different palettes are. And then I've got to run something to figure out, like, well, if you say the palette of boxes on the left, I think I mean this thing in my map that I've built of what's out there in the environment. So this idea that there's these symbols and there's stuff that's sensors, noisy. One of my friends calls this crispy, like these symbols, and swampy, perceptual data, these motor commands, these motor controllers driving around or something. Yeah.
How long does it take to train the forklift on startup?
It depends what you count as training. So the forklift as a project, I think took on the order of 3 years, and I think they probably had their first demo around 2 years in, and the project had, I would guess, around 30 people working on it. And they bought a forklift, and then they instrumented it with drive-by-wire so that it could be controlled by an algorithm. They put all those computers up there in the little machine room on the roof, and they put sensors. This is a LiDAR sensor, a bunch of LiDAR sensors and stuff. I can go look and see the timeline, but that's sort of the order to create it in person years. To train, so once it's been, so it takes a long time to make one of these robots. The Google Car project started, I mean, it depends. You count the DRC, the DARPA Urban Challenge, and then even before that, all of the research that went on, in all that time. The Google Car project has been going on, I think maybe 5 or 6 years. I'm not sure exactly. And it's a larger project in terms of person years. And where they are is like, so this was a research demo. They actually flew, I think they must have driven it down. They couldn't have, probably didn't fly it, down to Virginia from Boston and showed that they were able to operate autonomously in these environments. Google's doing something a little different because they want to make a product. So there's this long tail of bugs or robustness. And the mode that Google is in right now is sort of like NASA mode. Like they want to they want to make sure that every single system's got a fail-safe. So my brother-in-law at Google, he works on the car project. He's working on the low-level microcontroller that gets called if everything else goes crazy. So like it's going to basically have hardware that says like if everything else is going crazy, we want you to slowly bring the car to a stop and then stop. And don't worry about sensors or anything else. We just want you to stop. And then they have layers of control on top of that, right? So there's different fail-safes to say what happens, as the car encounters different environments and different things break. They want to make it robust to anything that could happen. So in the case of the forklift, when you bring it to do I'll talk about the language understanding system that we made. There's a training process that the user goes through. So you basically take it on a tour of the environment, and you show it where stuff is. So you say, here's the tire pallet, here's the box pallet, here's the ammo pallet, here's the truck. And you do that with the touchpads. You circle each of those on the map, and it trains up a little model and locates them in a map of the environment. And that takes 15 minutes for somebody to do. And then to collect this Amazon data, this data, this takes, it takes several iterations to get a good process, to get good data. You have to create these videos and stuff. Once you upload your Turk request, you'll get data back in about an hour. Or you'll start getting data back very immediately. Maybe about a day you'll have all your jobs filled. Then you have to annotate it. We'll talk about what that looks like briefly. And then you train it. So like the actual machine learning, it's a logistic regression. You guys did that. It's a logistic regression algorithm. The training takes 5 minutes once it's annotated. The big cost is like collecting and annotating the data. And then the inference it depends on how much we turn up the gain on it. So like if we are doing an evaluation where what we do to test our system is run it on these commands from our test set and see how accurate it's able to do. So when we do that, we tell it, search really, really deeply. Try really hard to find the best answer that you can. So that might take 5 or 10 minutes per command to complete that search. When we shoot the videos, we usually turn it up. We say, well, don't search so deeply. Just give us the best answer you can. We use beam search. So give us the best answer you can after 10 or 20 seconds. And we'll just do that. And typically, we try to make the environment small and rig things so that it works in a faster way. Does that answer the question? Okay, good. All right. And then people were already talking about like feedback loops, right? So if there's ambiguity, you want the robot to be able to detect the ambiguity somehow and do something about it, right? So you might want to ask a question like, which truck? If there's 2 trucks and you're not sure which one you're supposed to pick. So I sort of, in my research life, like broke this down to a couple of different subproblems. So like one is following instructions, right? So you put the metal crate on the truck, think about that, and then do the best you can, robot, to follow that command. And if it's wrong, it's wrong. We'll just check how many times we got it right and check how many times we got it wrong. So we did that, but then we were like, well, it gets it wrong a lot. What do we do about it? And one thing we could do, and people have, after us, went on to come up with better models and collect better training data in order to make the error rate lower. And that's really important. But what we did was we figured there's always going to be some errors. And what we want is to create this kind of feedback loop that some of you have already talked about. So we created this system where it can ask questions about what it doesn't understand. So it's doing this self-monitoring about how well the model is working. And then when there's high entropy in the distribution, when there's high uncertainty about what it thinks it should do, then it asks targeted questions to try to collect more information. And we showed that by doing this, we could reduce our error rate. So asking these types of questions enabled us to perform better at following commands. We also started thinking about sort of other direction of that. So like this is always, these first two are like the person is telling the robot to do something. Here we wanted the person to be able to tell the robot about stuff in the environment. So I showed this video a while ago, I think, of the semantic mapping where we were building a map of the environment with the sensors, but we also wanted the person to be able to say, oh look, the metal crate is in receiving. Go get it, robot. And somehow those words have to connect to what it already knows about where receiving is and what metal crates look like. So when it drives over to receiving, it can figure out what object it's supposed to pick up. And then the final thing we started thinking about is asking for help. So this is like when your robot gets stuck, what do you do? And really trying to think about what happens when there's one person interacting with a team of robots. So they're not really watching any one robot at detail. They're doing their own thing. And then when the robots get stuck, we wanted them to be able to like somehow explain to the person what the problem was so that they could provide help and then go back, the person could then go back to do whatever other project they were doing, maybe help a different robot or maybe do their own thing, like they're interacting with the robots in a kind of interrupt-driven way. So here the robot now, instead of the person talking to the robot's going to talk to the person and say something to get the person to do what the robot wants the person to do. So it's like in a more nefarious way, it's like our robot overlords, right? The robot's going to say things to the person. But I think it really helps when you've got lots of robots and one person and they can't track them all. So then the robot needs to provide this context. So looking at the time. So we'll talk about, we'll kind of go through them all at a high level. Maybe we'll dig into one in a little more detail. So sort of following instructions, the question that we were confronted with was how do we learn word meanings? And the reason we were confronted with this question was when we looked at the types of commands people were giving, when we really wanted to understand these ungrammatical sentences, we didn't want to limit ourselves. So if we were willing to limit ourselves to like a specific vocabulary and grammar, and there's definitely, like, there's nothing wrong with that. Like there's use cases where that's absolutely the right thing to do. Then you could imagine writing down word meanings, writing a program for the meaning of each word, and then teaching the people, this is robot-ese, this is what these different words correspond to, and this is how you should interact with the robot. But we really wanted the robot to be able to interact with anybody, so we didn't want to restrict their language. So we said, we're going to learn word meanings. So how would you guys do this with what you know from AI? How would you start?
At the very least, you need a set of training data.
Yeah, some training data. So what would the training data look like? Somebody else. What might you collect for training data for these word meanings? So, yeah. Yeah. Yeah, so you might like take pictures of what the robot sees or somehow represent what the robot knows about the environment and then associate that with words. Yeah, so like this idea that so it's kind of like for machine learning, like you got labels, you've got your features, and you somehow want to associate them together. And where might you get that data? Yeah, right. So you might have a person do the task. So you could have a person drive the robot around, or have the person label what the robot's doing, and somehow get language associated with that. And this translates to lots of different things. You guys have a question? Yeah.
If the robot have English, can the robot Google it? Get actual
Yeah. Yeah, so that's actually something people are really excited about. So like when it gets stuck, you connect to the cloud, and you have somebody in a call center come into your robot and get it unstuck, and then go on to the next call. And I think that's gonna, like when we get robots in our homes, I think that's gonna be a crucial capability for them to have, because otherwise when it gets stuck, you're gonna have to unstick it, and that's gonna get old real fast. Chad at Jenkins at Brown is thinking a lot, as I said, about that type of interface, like the robot call center. It calls in, gets supervision, and then it saves that, right? Because then that's a training example. This is what you should do to get unstuck in this situation. I'm going to stick that in my giant database on Skynet or something. And the next time a different robot encounters a similar situation, it can use that to figure out how to get unstuck. So people are thinking about lots of different ways of collecting this type of training data. So like that's one example, like get a call center. Another example is see what people do. Maybe there's no robot, but like let's watch how people drive cars. And then see if we can learn from that how our robot should drive. Where maybe it should learn to stay on the road and not go on the shoulder by watching what people are doing in the environment. Where people do things like watch where people walk through environments to learn, what are the typical places to go? How do you avoid conflicts? Like if somebody learn to stay to the right when you've got a busy hallway and stuff, and then use that to control the robot's motion. And people do crowdsourcing types of data, so like going on to Amazon Mechanical Turk. That's what we did, but it's not the only thing that you could do. And you have to be creative about it because it's hard to get data, and yet data can help. So what we did was we showed people videos of the robot doing something, and then we paired the video with words in an unknown language. So when I do this slide, I usually show the language as Polish. That's because my husband's Polish, so I have an access to a Polish speaker who can give me the Polish sentence. And what this does is kind of gives you a sense of what the learning problem really looks like. Right? So you have these words, załaduj towar na ciężarówkę, and you have the robot doing stuff, and you have everything the robot knows about the environment as it was doing stuff. So like this robot knows about the truck, it knows about the pallet, it knows that it's doing a high-level action of putting the pallet on the truck. And then we try to somehow use that as supervision for our model. We don't just give it one example of this, we give it lots of examples. So here's a bunch of different videos with a bunch of different translations, or glosses in language. And we're going to try to learn from this what these words mean so that the robot can follow commands produced by people. I think it no, it doesn't. So our work is actually in English because there's a lot more English speakers than there are Polish speakers, and because I know English better than Polish, so it's easier to debug your system. But I like to show it in another language because it really gives you a better intuitive sense for why this problem is hard. Because that's really what the robot is looking at. It doesn't know what those words mean in advance. Whereas when you look at it, you know, so it somehow makes it feel easier. So I think I've showed this sequence before. But then the problem is like, well, what should the robot do? And we might imagine some search space that we define about different actions it should take. And we defined the search space very carefully so that it wasn't too large, but contained actions that were sort of relevant to a forklift. And we formalized it as this argmax over action. So here gamma is the action that you want the robot to take, and f is your objective function. So this kind of looks like our algorithm for all of AI, right? Like we're going to search over different actions, we're going to score them somehow, and then we're going to execute the one that has the highest score. So that argmax pulls out that gamma and says, this is the one you should do, robot. So then the question is, well, where do we get f? Where do we get f? It's a cost function. Yeah, so f takes as input the words, the command, and this action that you want the robot to take. So what data set where we were instructing the robot on where to go in an indoor environment. So we would say things like, go down the hall, and then go to the elevators, and then take a right, and then go past my office. We saw a different pattern. We saw that this red continued on past the object. And the reason was that most of our examples, you would go to the elevators, and then you'd go past them. And so it didn't really matter. Like, trajectories that went a little past them were OK, because you're going to keep going in these different situations. OK. So that's sort of like, go to the truck. The problem is that we wanted our system to generalize, right? So if you go back to like this language that we showed in the example, like they don't just say go to the truck. So we did all this work of all this data to learn go to the truck. But now what happens if they say go to the pallet instead? What's our system going to do? Yeah. Yeah, so we need to collect more data for the pallet. There's all this data for go to the truck, and then we collect another set for go to the pallet. And we could keep going for every single noun phrase that you could go to, which is a lot, right? Like you can go to a comet. That's what happened like last week, right? We sent a robot to a comet. You can also, a little snail can go to the leaf of lettuce in your garden. It's a few inches. So we didn't want to do that because it would require us to collect a lot of different data. So what we did was generalized our model so that we were doing inference over all of the different things that a person could say. And so then you get this ability to handle these complicated structures because we can create a random variable in our model for each linguistic constituent. So now I'm going to kind of jump to a higher level because I want to talk a little bit about the other stuff. But the short story, if you do this, is you get these graphical models for different commands that factor according to the structure of the command. So we would walk through the structure of the sentence, and we create a graphical model. This is a factor graph. It's kind of like a BayesNet, but a little different. So we create a graphical model with random variables and factors defined by the structure of the language, defined by that parse structure. So if it couldn't parse, we'd be in trouble. We'd make the wrong model. And then we'd use this in order to run our inference. So that would let us train on sentences. I think I have this example here. We could train on sentences, like put the pallet on the truck and go to the truck, and then test on a sentence we've never seen before, like go to the pallet. And it would make a good guess, because it would know, well, I know what the pallet means, and I know what to means, and I know how to combine them together to get the meaning for that whole sentence of go to the pallet. We get this compositionality of language. All right. Now I'm going to skip. We evaluate it. It works to some degree, not all the time. I think I showed this video of me talking to the forklift, put the tire pallet on the truck. And from now to when it starts to move, that's about how long the inference takes. So now it's done thinking and it's executing when we've tuned it for demo mode. This is showing the graphical model that we created. And it's kind of driving. It's been given that tour of the environment before in advance. It drives through, it picks up the pallet. And drives over the truck and puts it on the truck. And this is all learned from the crowdsourced data from Amazon Mechanical Turk. OK, yeah? Yeah, so we don't want the forklift to drive too quickly, because it's kind of scary. I don't know if you see when it's moving, you can kind of tell it looks a little top heavy. Like we really don't want it to tip over. And it takes time. So like when it's standing right in front of the object, you can kind of see. I don't know. I can't speed the movie up. We just watch it over again. You can kind of see it's moving its forks up and down a little bit. It's got a little LiDAR on the forks. And it's basically scanning, by moving its forks up and down, it's moving that LiDAR up and down right there. See how it's tilting it back and forth? It's tilting it to see exactly where it needs to put its forks so it doesn't hit the object. And the same deal when it gets over to the truck. It's like scanning up and down to see how high it needs to go as it's doing its thing. Yeah?
Did you first, before building it into the actual forklift,
Yeah.
tests and everything. So in this instance, what's really the benefit of then actually bringing it to a robot? I know when you kind of go into like
Yeah.
industry, like we want room
Yeah.
and cool stuff like
Yeah.
that. But
Yeah.
what changes and why do we actually?
Yeah, that's a
test
really
it
good
with a
question.
real robot?
Yeah, it's a lot of work to make it run on a real robot.
Yeah.
And a lot of that work, you can't really write a paper about it. Like you can't, and it's not like there's this new knowledge that you can crystallize about making it run on a real robot. I think it's really valuable to do it though. And the reason it's a little bit more intangible, but there's a few things. So first of all, there's something really cool about seeing what this actually would be like if you have it on a robot. There's things that you just can't simulate, like actually standing in that parking lot and talking to the forklift and having it go and seeing in a really visceral way, wow, like it takes 20 seconds, that is way too long to be waiting to have it run on the real robot. The other thing is it's really easy to fool yourself if you're in simulation. It's really easy to be solving the wrong problem. So you can write a really nice paper, come up with a really beautiful algorithm, and get awesome results. But when you and say the rest is left as exercise to the reader. But then when when the reader tries to put it on the robot, you're laughing, right? You know there's going to be surprises. You know it's not going to go the way that you think it's going to go, and that serves as a stimulus for me anyway. It's like a check, like to make sure that this, like it's an existence proof. This model that we created of how we think the robot works. It's faithful enough that, look, we actually got it to run on the robot. And as we were doing this, like we were able to identify areas where it didn't work. And that has sparked a lot of the next things that we're going to talk about. So like the question asking work that I'm actually comes up next was motivated by examples from the real robot. So like here they're saying move the pallet from the truck. That we probably could have gotten from simulation, like using ambiguous language. But this one, like offload the metal crate, our robot doesn't, our forklift, our real robot does not know metal crate. We do not have a detector for metal crate or for silver container. We could not get those colors out. So this is an example of problems that we might not have ever even known about unless we had put it on the real robot and thought about what those implications were. And there's other examples that motivating work that we're doing now. So like this we got from people, but we watched a human expert forklift operator instructing a human trainee. And what was striking to me about that was that they would say things like, drive forward 6 inches and then tilt your fork back a little bit. Okay, now put it on the truck. And then at the highest level, people would say things like, okay, unload that whole truck. Move everything in storage A to storage B. And the problem that we were struck by was that if we wanted our robot to understand drive forward 6 inches or move out of the way, and we also want to understand put the pallet on the truck, and we also want to understand unload the truck. And you can think of examples in the house too, like move out of the way, get me a glass of water, clean up my kitchen. These very low-level actions and these very high-level actions. If you define the search space in terms of the low-level actions, you'll never, the depth of those high-level actions and the branching factor is going to kill you. You'll never find the high-level actions. And so that's motivating our research in Minecraft that I've talked about, trying to figure out how we can plan in those really big state spaces. Because if we can plan, then we can understand language. And we know from our experiments on the real robot and from our studies of real potential users that that's something that we care about. Okay. So one next thing that came from doing on the real robot was like, it doesn't work all the time. We want to ask questions, right? So like, we wanted an approach that enables our system to identify uncertain parts of the command, ask targeted questions, and then use information from the answer in order to figure out better things that it should do. So what we would do is we'd have this distribution in the robot's head over the object in the environment that it's talking about. And it's uniform here, so entropy is high. So then we would ask a question like, what does the metal crate refer to? And then we would get an answer, and then we would use that to do an update. This kind of looks like a Bayes filter style thing, right? Like this recursive form that we can repeat until we're pretty sure, and then we can go off and do the action. And the key thing was that we wanted our model to be flexible. So if you say something like, put the pallet on the truck, and there's 2 trucks and 1 pallet, you want to ask about the truck, versus 2 pallets and 1 truck, you want to ask about the pallet. And so by using this entropy-based metric, we were able to get this type of behavior to happen. So the robot would use its sort of model of what it understood in order to ask these targeted questions. I'm skipping the math because we're out of time. But like it basically translates into these graph edit operations when you incorporate information from the answer. And then we have this evaluation. You can read the paper. It's all on my website if you want, where we showed that we got better performance by asking targeted questions than we did commands only. We got half of them right. If we asked questions randomly, we did better, but not that much better. If we asked 2 targeted questions, we could get up to 77% right. So we could see a significant improvement in accuracy by asking questions in this targeted way. Yeah?
What are the failures like?
What are the failures like in
this data?
this data?
Failure like, oh, it just goes straight into the truck.
So this is simulated data, actually. So we took the problem from a real robot problem. We actually never ran the system on the robot. The failures are things like, so like in this example back here, it would just pick a truck randomly. So it would put something on the truck, but it would be the wrong truck. And it might be because they said, like our Torker data might have just said the truck. They didn't tell you which truck. You didn't know which truck. So there'd be no way to figure it out. Or they might have used a word that the robot didn't know. One of my favorite examples of that is somebody said in our data, they said, pick up the lonely pallet, which was very poetic, but never appeared in our training data. So when we got that in test time, then there was like 5 pallets, and like we just picked randomly. Whatever one happens to come out first in the search, because they were all the same according to the model, was the one that it picked up. Yeah?
Are you running this situation if the robot tried to put the truck on the pallet?
Yeah, that's good. So like, so that tended not to happen, and the reason, partly that didn't happen because we defined our action space to say you can't pick up trucks, robot. Don't try. Just don't do it. It's a bad idea. But partly it didn't happen because the meaning of put, the things that it learned tended to be about picking up small things and putting them on big things, and not the other way around. And so that was bad. That's bad because maybe it kind of biases you towards forklifts. But it's good because it would like not really be too excited about picking up trucks. If we had a more general framework, like that definitely is a concern. And so like you guys talked about bag of words models for spam filtering. So like an example is like pick up the box palette that's next to the ammo palette. If you're using bag of words, there's no way to decide between those 2 palettes. So you really need this structure, this parse structure that you get from our model. Okay, I'm going to skip more stuff. I really want to talk about the failure. So we're going to go, you've already seen this video of understanding statements. The last thing I wanted to talk about really quickly was asking for help. So this is the idea that there's robots that are assembling furniture. This was work done by my collaborator, Ross Knepper, who's a professor at Cornell, assembling furniture. There they go. But what happens is these robots fail a lot. So here's an example of a failure. It gets stuck. The path planner gets kind of stuck in this infinite loop. And what's going to happen is, oh no, the video didn't play. There it goes. Is Ross is going to help. That's Ross. He's going to help it. He's going to kind of shove the robot, right? And then it goes. It figures it gets unstuck out of its little loop. And yeah. The reason he knew what was helpful in that situation is because he made that entire system. Right? He knows everything about that system. He's seen that failure a lot of times before. He knows what's wrong, and he knows even when it didn't work the first time, he knew if he shoved it harder, it was going to get unstuck. And it does. Like it gets unstuck. But the problem is when we let our robots out into the wild, we roboticists can't go with them and shove them when they need to be shoved in order to get unstuck. And a lot of the help they need is as simple as shoving the robot or restarting something or moving something so that it's in reach or turning some lights on so the camera works better. So that was sort of motivating our work on making the robot, I'm skipping more stuff, ask for help. So like saying things like, hand me the white leg that's on the table, so that a person who's in a cluttered environment, who is not Ross, who does not understand what the robots are doing or why they're broken, can figure out what actions to take to provide help. So I'm going to stop here. But if you're interested, you can read our paper. It's the RSF paper we presented this summer. And it kind of closes the loop between understanding and generation at least in isolation. And the thing that I'm working on now in my group is trying to have it be all happening at the same time in the same system, so that one robot can understand language, can ask questions, can ask you for help when it needs it, and interact with you using language and gesture as if it was another person. Thanks, guys. Have a good Thanksgiving.